So previously we looked at probability distributions. We examined distributions for variables that are categorical, either coin toss or blood type or quantitative. So remember that categorical is a variable that just has a name. It doesn't have a number associated to it. Like the number of boreal owl eggs in a nest, it was always a number, right? But the blood type, you can't give a blood type a number. We don't use numbers to describe them. We use letters or names. If the variable is quantitative, which can be described with a number like the owl nest, the number of eggs, then we can describe the probability distribution using shape, center, and spread. So we wouldn't use that for blood type or those type of categorical data. But in the next example, we'll see how a comparison of probability distributions can help detect tax fraud. Now here's our example. In this example, we will compare probability distributions for legitimate tax records and for fraudulent records using shape, center, which is mean, and spread, which we'll use standard deviation to calculate. We will also use empirical probability distributions from data and a theoretical probability distribution from a mathematical formula. The variable is the first digit in the reported income on tax returns. The variable values are the digits 1 to 9. For example, suppose the income reported on a tax return is $20,713. The first digit is a 2. Tax returns with reported income from $4,320 or $43,000 or $492,565 will all have first digit 4. When we examine a very large number of tax returns, we can calculate the relative frequency of the first digits to determine an empirical probability distribution. A professor of accounting, Mark Negrini, I hope I said that right, used data from 169,662 IRS files to calculate relative frequencies, aka empirical probabilities, in the table below. So this table shows what the probability is of, for example, your income tax, or your income being, starting with a 1, the first digit, 0.305. What if it starts with a 2? It's 0.178, and on, 3, 4, 5, 6, 7, 8, 9. There's no 0 digit because if the first digit is a 0, we just ignore it and move on to the next one. Okay, now let's check our understanding of the probability distribution. For example, if we randomly select a tax return, there is a 30.5% chance that the reported income has a first digit of 1, because we see that here in this table. The first digit is represented in the first the first row of this table. The probability of that digit being your first digit is below it. A reported income beginning with the digit 9 is much less likely, with a probability of 4.5%. Surprisingly, the empirical probability distribution from Negrini's data, I think I said that right, I hope, is almost identical to a theoretical probability distribution generated by a mathematical formula called Benfold's law. We can see this in the table below. On the table we see the comparison. So for example, in the very first column here, we still have the same row, the same first row, the first digit being a 1 in your tax return. So we'll see that the second row represents the exact same second row. So far the table is the same. It's only that third row that they've added something new. This is the probabilities that were predicted by Benford's law. Probably something way complicated. But look how close it was. The theoretical and the empirical were very close. Like I said, the second row, the middle one, is empirical because these were actual tax returns. They counted how many there were out of the total, and they got these probabilities. But Benfold's law somehow calculated what they thought would be the theoretical probability, and it's very close. So for the second digit being a 2, these are only off by 0.002 probability. Oh my gosh, that's crazy. And then the first digit of your tax return being a 3, very close as well. All these values are very close. So in case you're interested, the formula for Benfold's law is probability of D, I think D meaning the first digit being, D standing for digit. The probability of a certain digit would be log or logarithm. You might have seen that in an algebra class, or if you take another class, you might see it again. Logarithm, you have that on your calculator, of 1 plus 1 over that digit. And if you're not curious, don't worry about it. Yeah, that won't be on the test. It's just if you're curious. Now, where did this guy come up with this formula? Now, that's more interesting, I guess. Probably way above my head. Below is a histogram of the theoretical probability distribution for first digits based on Benford's law. We can see that the probabilities are right skewed. Let's look at that. We use technology to calculate a mean for the first digits and a standard deviation. The mean is approximately 3.4, marked with the blue line here, with a standard deviation of about 0.25. The lines on the left and right indicate one standard deviation below and one standard deviation above the mean. So most of the data is likely to be somewhere between 1 and 6. It looks like. I think that's what they're trying to say. Yeah, here's the mean. And then here's one standard deviation above. Above, I'll say plus. And then here's, this line represents one standard deviation below. I'll put minus because you're going below. Okay, now let's look at fraudulent tax returns. Will fraudulent tax returns display a similar probability distribution? By comparison, below is the probability distribution for first digits in fraudulent tax returns from a study of fraudulent cash disbursement and payroll expenditures conducted in 1995 by the District Attorney's Office in Kings County, New York. For fraudulent data, the probability distribution is more symmetric. The mean is approximately 5.2 with a standard deviation of about 0.9. So look at the difference between this distribution and this one. They look completely different. Obviously, the relative frequencies of first digits from the fraudulent data do not follow Benford's law. This probability distribution has a very different shape, center, and spread, mean being the center and standard deviation being measuring the spread. Compared to legitimate tax returns and fraudulent data, we are much more likely to see numbers with the first digit of 5 and much less likely to see numbers with the first digit of 1, 2, or 3.